So, we will continue with our discussion on heat conduction, and if you remember yesterday in the last lecture I wrote the governing heat conduction equation or the energy balance equation in 3 different coordinate system. I discussed some concepts in the context of both the cylindrical as well as the Cartesian coordinate system, and I want to introduce some important aspects with regard to the spherical geometry. So, we will consider now the same philosophy continues. We will consider 1D and we will consider only radial transport, constant property, and of course, as I have said that we will go for steady state. So, the governing equation that I wrote, which had 3 different terms, one is the unsteady term on the left hand side, equal to on the right hand side I had the divergence term, okay. Or the gradient term rather of temperature, and there is the heat flux terms basically, and I also had the volumetric rate of heat generation. Okay. So, if we now apply this simplification, the spherical r, theta and phi as a coordinate system, the governing equation that I had written in terms of the unsteady terms, the second order derivative terms and the heat generation term, that is going to simplify to this particular So, let us now, as I said, that always when we write an equation, we have to depict the diagram or present the diagram. Okay. So, that is the sphere, and you can imagine surrounding to be, we are considering a spherical geometry about this sphere, which has a radius is equal to r0. So, that is the radius. And then we can take a control volume here, and then this is our, as I have said, far away from the surface of the sphere. So, we are approaching infinity, and we have obviously the bulk or the surrounding temperature as the far field temperature in this particular case. It is a steady problem. So, the problem is like the sphere is there. It is maintained at a constant temperature, and that constant temperature is T sub 0 at R sub 0, and I want to find out between R0 and infinity how does the temperature varies, and that is the equation which is going to now describe the temperature field as a function of R, and this represents the radial coordinate system. Now, this equation will in one go show us that k r square, this is constant, and our favorable nomenclature is constant is represented by beta, and what we see here that minus k dt dr, which is equal to beta divided by minus beta divided by r square, and this is the heat flux at any point. The heat flux here, everywhere it applies, and this shows that while beta is a constant, the flux varies inversely to the square of the radial distance. Now, from the Fourier's law, we had this expression which I have discussed elaborately in the context of cylindrical geometry. So, if we integrate this, then we have minus k integral dt, and then we have the limits here t is equal to t0 to t infinity, and here I have from r0, r is equal to r0 to r is equal to infinity. And if we do this, then we have substitute here qr, and what is that qr? That is the value of qr, minus k dt dr. So, this is going to be minus beta by r square, and this is to be now can be integrated between the limits r0 by alpha is equal to, this is going to be minus k into T infinity minus T 0. Straightforward integration. So, absolutely no problem, and here we can see that this is going to be, if you take out b, then this integral is itself going to be minus. So, it is going to be basically, if you take the minus beta out, then this integral is going to be like this, and this is r is equal to 0, and this is infinity, and this is equal to k T infinity minus T 0, which is from here I can straightforward get the value 1 by infinity is going to be equal to 0 minus of this. So, we are going to, this minus and this minus is going to cancel out, and what we are going to get now is equal to beta is equal to k into T infinity minus T 0 into R 0. That is the value of beta. So, the radial heat flux here I can substitute here. So, we can bring it. So, this is minus k T infinity minus T 0, and that is R 0 divided by R square. What I have done, I have got the value of beta, and this I have substituted into the right hand side, and I have got the heat flux value. And here what we can see that we have the flux. If you want to now evaluate this flux at any point r, because it is a function of r, as you can see, I want to now evaluate the flux at the surface. So, what I am going to do now is I am going to, that is the way we write it. So, the flux to be evaluated q r at r is equal to r 0 flux. So, that is equal to minus k derivative of t with respect to r evaluated at r is equal to r 0, and then I will substitute in this expression r is equal to r 0. So, this will give me k times r 0, and this is going to be T infinity minus T 0. Or I can say this is equal to, one further step, I can now reverse the sign. So, T 0 minus T infinity. Now, I want to introduce one expression here. And if you remember, I said that when I was talking about the governing equation, and that in that context I was trying to tell you about the possible types of boundary conditions. I said that there could be two types. One is the given temperature, the other is the given heat flux. The given heat flux again has two categories. One is the heat flux is specified, or in the other case the heat flux is specified in terms of a heat transfer coefficient and the surrounding or an ambient temperature. Let us suppose that the flux is specified in terms of so that is the heat flux at surface. This is the surface heat flux. So, this H is the surface heat transfer coefficient, okay? And this is the temperature, ambient temperature we am talking about. So, therefore, this is equal to this. So, if we equate this K R 0 T 0 minus T infinity, then what I get? I get H I made, I think, a mistake here. So, R 0 square. So, we will put it R square here. So, H by K R 0. So, therefore, heat transfer coefficient K R 0 T infinity, and then we can get here, this is going to cancel out, and we should get, let me see, 1 r I think somewhere I have missed here. So, this is beta. So, this r is going to go here. So, this is r 0, and this is going to be q r, and if we do it, so this is going to be r 0. So, therefore, this is r 0 divided by r 0 square. Yes. So, therefore, we can say that this is r 0 square. So, from this, from here only I will write flux evaluated. So, this is the moment. So, this is absolutely fine now. So, this R 0 and square will cancel out, and therefore, I am going to get H R 0 by K is equal to 1. These are characteristics, or I can say that the same expression can be written as H d, where d is the diameter, by K, and this K is a thermal conductivity. Now, let us see what is this thermal conductivity. Is this the thermal conductivity of the solid, or it is the thermal conductivity of the fluid? It should be the thermal conductivity of the fluid, okay? Because the sphere, solid sphere is here, and this surrounding is the ambient. So, therefore, this is the ambient medium in which and where only heat conduction is taking place. It is a stagnant medium. There is no convection which is present in the system. It is a pure diffusive heat transfer. And I must say that whenever we write the Fourier's law, for example, we say basically it is a heat conduction or heat diffusion process, because the characteristics of a diffusion process is that it obeys always a gradient type of law, whether it is Newton's law of viscosity, whether it is mass diffusion, or whether it is heat diffusion. Diffusion always obeys a gradient type law. So, therefore, this term now is going to be equal to 2, and this parameter, which represents basically the ratio of heat conduction to heat, if you say that this is a dimensionless parameter, obviously 2 has no dimension here, and this dimensionless parameter in heat transfer is known as the Nusselts number, and the suffix d essentially implies that it is a diameter based Nusselts number. So, this basically tells us that the strength of the convection to diffusion, because K is the property which is causing here diffusion of heat through the surrounding medium. So, the strength of the convection to diffusion is basically is equal to, because if you multiply K into delta T, that is what you get the heat flux. If you multiply with this, then also you get what you call so H, you take out R 0. So, K by R 0 multiplied by delta T, that becomes the conductive heat transfer, and H into delta T, that becomes the convective heat transfer. So, this number, Nusselts number, basically tells us that it is the ratio between convective to conductive heat transfer. So, that means in convection dominated system, had there been a strong current here, the value would have been much greater than 1, because the numerator would have been in that case significantly larger, but the value is 1. This is the limiting value possible, a pure diffusion case or pure heat conduction case when there is no fluid flow which is present in the system. Now, in contrast to the scenarios that I have discussed so far, there could be a case where, for example, the body may have very large thermal conductivity and it may exhibit a negligible gradient in all directions. Now, in that particular case, then what happens is we had this governing equation. I am taking the liberty to write it in Cartesian coordinate again, and this is, I am writing it for constant thermal conductivity, and then this is my governing equation. And what happens is that this term, the gradient of temperature, when the body has very large thermal conductivity, which essentially means heat will be able to flow very quickly, and as a result of which the gradient of temperature will vanish. So, therefore, bodies which exhibit a large thermal conductivity, this term can be, or we say such bodies are the bodies which exhibit negligible internal temperature gradient. So, in that case, the temperature, which initially used to be a function of x, y, z and t, now becomes a function of t alone. And we say that now the long parameter model can be applied. Okay? In these cases, there are special variations. From point to point, there is a flux variation. From point to point, there is a temperature variation. But when we will talk of a lump parameter model or a body with negligible thermal conductivity, a very high thermal conductivity, in that case, what we are going to see that basically we have this term is going to vanish out, because the body will have no internal temperature gradient. So, under that case, what happens is we have a number which we say, which characterizes this. So, there is another number which looks like Nusselts number, but h is the heat transfer coefficient, d could be the diameter, and then we have k which should be solid. So, this number we generated as a bio number, and the spelling is BIOT. Okay? So, the bio number essentially gives us, so a small bio number, large thermal conductivity of the solid, or a very small bio number will essentially tell us that within the solid there is no temperature gradient itself, and in that case we should be able to apply the lump parameter model, and it becomes a very simple case. For example, you can integrate this equation if this parameter is given. Suppose, I am taking of a sphere here, and there could be another sphere which could be heated, okay, and as a result of which is maintained at the same temperature. And then what I am saying is this body has a very large thermal conductivity. In that case, we can say that from here to here there is negligible temperature gradient. The body has a constant temperature as such, provided the bio number is very, very small, or the thermal conductivity is very, very small. In that case, integration of this will require only one single condition, that is that T is equal to 0. You will require that what is the initial temperature given in the system, and then you should be able to march the solution in terms of time and get as a function of time how the temperature is changing within the solid. But note, under that condition you will have temperature here, and temperature here. All are going to be identical. The special variation term has vanished because the thermal conductivity is very, very large. Let us move on and talk about, before I start to talk about the unsteady state, I will say that, for example, 2D scenarios are, equivalent 2D scenarios are not so much of practical implications. For example, I would say that steady state temperature, because steady state temperature field that I have so far discussed is to introduce to you certain concepts like, heat generation term, then the contact thermal resistances, then dimensionless number like Nusselts number and bio number. So, to introduce these concepts and to show you that analytical solutions are possible, that is why I have discussed in the ambit of the Cartesian coordinate system, spherical coordinate system, as well as cylindrical coordinate system, how you can manipulate the governing equations. But as such, practical scenarios are never one dimensional, they are more than, they are three dimensional, they are unsteady, and so on and so forth. So, for example, if I now tell you that, look, I am interested to know, I have a two-dimensional slice, okay, and I want to know that what is the steady state temperature, given that this boundary temperature is 1, this boundary temperature is 1, this boundary temperature is 1, this boundary temperature is 1. It is a trivial solution, because if the boundaries are maintained at all the boundaries at 1, we will have a steady state solution where everywhere the temperature field is going to be equal to 1. Even if I say that, look, I do not have to solve the equation. If this surface temperature is 1, okay, maybe 1 is in terms of dimensionless temperature. Okay, I will introduce that dimensionless temperature when I talk about the unsteady state heat conduction. Now, if I have, in this kind, if I have different boundary conditions, but if I tell you that, what is the kind of a temperature that I am going to expect, I do not have to solve the equation, and I can say that this temperature at the center of the square plate could be 1.5. So, these solutions are steady state solutions are not so important, but the same problem, make it unsteady, it will have a lot of practical applications. For example, you may have a slab which may be in the furnace, you are bringing it out, it is cooling down in the surrounding, and then the temperature is changing as a function of time. In that case, the problem may be treated as one dimensional, the problem may be treated as two dimensional, but the main issue is that the temperature is changing as a function of time. So, therefore, the true problems under the for all practical scenarios really warrants that we deal the unsteady state phenomena rather than the steady state phenomena. Okay? The steady state temperature fields are like a temperature field which one will see at a very, very long time. For example, if I now bring a slab, hot slab at 1000 degrees centigrade, and keep it in this particular room and come back tomorrow to find out that what is the temperature. So, which I call as a long term solution, long time solution. Okay? So, I will see that the slab has cooled down and it has attained the room temperature itself. So, I do not have to do any calculation, write any equations. I can say, sir, after 3 days you can come and you will find whatever is the room temperature, that is the slab temperature itself. So, it is not, but how long will it take from 1000 degree to come to the room temperature is a parameter of interest, and that warrants that we deal the subject of heat conduction not for under steady state, but rather under unsteady state condition. Now, let us look at the unsteady state heat conduction phenomena. And here we can do it in 1 dimension, 2 dimension, 3 dimension. Some of these equations, some of the expressions that I will write, the analytical solutions are easy. There are multidimensional problems, the analytical solutions are complex, but nonetheless, even for a unsteady 2-dimensional, 3-dimensional cases, one can find out the analytical solution, which may be a little tedious under certain simple boundary conditions. Okay? If the temperature at all the boundaries are identical and so on and so forth. So, it is possible to find out an analytical solution even for 3-dimensional scenario. But all the cases which are amenable to analytical solutions, I do not have the time to discuss today. Possibly could be the last lecture on heat conduction. I have to wind up. Okay? So, therefore, I would say that if you are interested to know analytical solution of class of heat conduction problem in different direction, different types of boundary condition, there are excellent textbooks which are available, which I have not of course cited in the hand circular that I have given you in the first lecture. So, you can look at the textbook by Karslow and Geiger. So, that is a huge, it requires a lot of mathematical expertise in order to find out how multidimensional, you have to know, for example, techniques like Laplace transformation, you have to know separation of variables and so on and so forth. So, it's a highly complicated maths is involved, excuse me. Then you can read the book by Ojicic, that's also a good book, and you can also read the book by Holman. So, these are all standard texts which gives a plethora of solution for unsteady state cases, and here we are going to discuss only 1 or 2 only to give you the flavor of the subject and not quite comprehensive presentation. So, let us now look at, so we will do it unsteady state heat conduction, and we pose the problem 1 day, but it is unsteady state. We still continue with constant property. No heat source, and I will demonstrate that this discussion with reference to Cartesian coordinate system. That is the problem definition. And then now let us see. So, if you look at the governing equation now, the governing equation will look something like we will write it 1 dimensional. So, it is one could write x also instead of y, z also. Let us now depict the geometry. So, this is my y direction suppose, and I am taking it 1 dimensional, and this is the domain. Visual depiction is very important when you solve the problem. So, you have to, the moment you write the coordinate axis, okay, you draw the geometry, the problem becomes very, very simple. Now, I have provided the governing equation, I will provide the boundary condition. So, what I am saying that this slab, this is the slab geometry, one dimensional, which is infinite in this way and which is infinite in the direction perpendicular to the board. Now, this has, as I would like to cast it, a width of 2b and if this represents y is equal to 0, then obviously this surface represents plus b and this surface represents minus b. So, this is the geometry and I say that initial condition that I am going to apply here, that is at t is equal to 0 for all values of that is the entire domain of the slab and I say that t is equal to t0. And boundary condition t greater than 0 at y is equal to plus minus b at both the surface t is equal to t1. That is the problem. So, that means this slab is initially at a temperature of T0, you can assume it is at 25 degrees centigrade. All on a sudden, both these surfaces somehow has been increased to T1 temperature and I want to now find out that how does temperature within this domain changes as a function of y. That is the task in which rho Cp K, the thermal conductivity, is known and I can also write this equation. If you remember the definition of thermal diffusivity that I have introduced as alpha, in which K by rho Cp is the thermal diffusivity. So, that is also one possibility. Many times it is good to work with a non-dimensional form of the equation, because I have posed the problem. As far as posing the problem is concerned, there is no uncertainty. It is a clear-cut problem with equations, the drawings, the boundary condition, initial condition, etc. But if I convert the governing equation into its non-dimensional form, then what I can do? I can generate the temperature field or I can generate the non-dimensional temperature field in terms of numbers 0 and 1. So, non-dimensionalization of equations are basically and boundary conditions are done in order to demonstrate problems which otherwise for which otherwise numerical values cannot be obtained, and this allows us to obtain the field distribution of the dimensionless parameters in terms of certain specific values, and that range of the values is 0 and 1. Now, in that context, you remember that I have not shown you explicitly, but I said that when I wrote the Navier-Stokes equation, which contained inertial force, viscous force, gravitational force, as well as pressure forces, I said that this equation, since each term is force, if you divide it by one force all through, in that case you can get the equation in non-dimensional form, and in that context I said that we get Euler's number, Reynolds number and Froude number. In this case also we can define, we can non-dimensionalize this equation. So, every equation is a dimensional equation, the way I have put it, we can non-dimensionalize, and I can put a non-dimensional temperature as T1 minus T0, T divided by T1 minus T0. This is no way fix. You can find, you can write T minus T1 also is possible. There could be many possible, but you see this is temperature, and that is what I say, that theta represents my non-dimensional temperature. The moment I do this, then what happens is, look, this boundary condition will become now theta is equal to, if I put T0 here, then in terms of non-dimensional variable, this becomes. So, my boundary conditions now change from initial condition is 1 and then the boundary condition is 0, okay, in terms of the non-dimensional variable. Let us say that we introduce another non-dimensional parameter, which is the non-dimensional distance, and that distance is going to be y divided by b. So, therefore, what happens now? When y is equal to plus b, this will be plus 1. When y will be minus b, this will be minus 1. So, this term will vary from equivalent to writing greater than plus 1 and less than minus 1. That is the modified boundary condition. And then this term therefore represents the non-dimensional distance is equal to plus minus 1. I am writing it in different colors so that you can distinguish. Now, two parameters are there, and then I say that we introduce another parameter which we call the non-dimensional time, and this is so when t is equal to 0, therefore I can say that I can write here tau is equal to 0 and this is tau is greater than 0. So, I have transposed the equation, and if you substitute this here, then what you are going to get is you are going to get, I will make my life simple here, or maybe I will not do that. So, this is the same equation will look like now. I will write it with a red chalk. So, partial that is the non-dimensional equivalent. So, I am not doing the substitution and showing it, you should be able to check it for yourself. And this is the non-dimensional heat conduction equation, in which the theta represents the non-dimensional temperature defined the way I have defined it, tau represents the non-dimensional time defined the way I have shown it here, and eta represents the non-dimensional distance. And those which are written with pink chalks here represents the non-dimensional initial and boundary condition. Now, which essentially tells us initially we had t as a function of y and t, and now once we have non-dimensionalized, we have theta as a function of eta and tau. That is what it is. So, all parameters are rendered between 0 and 1. Okay, the distance is between minus 1 and plus 1, and the variables will come out to be in the range of 0 to 1, because initial condition is 1, boundary condition is 0. So, at all time the temperature, non-dimensional temperature will vary between 0 and 1. There is no heat source to take the temperature beyond that particular range. So, now we want to discuss about the solution of this particular equation. The solution, basically these are called product solution techniques, that if theta is a function of eta and tau, then it says that the solution will come out to be in terms of one function which is eta and the other function which is f2. This is called the product solution technique. So, you can read any of the Karlsruhe-Geiger, for example, and you can see how the product solution is really done. Okay. So, two independent functions in this case, because the derivatives are different, one is with respect to the space, other is with respect to the time. One has a second order derivative, the other has a first order derivative. So, therefore, these functions are going to be different, and if I write the solutions, we will see that this function will come out to an exponential function and this will come out to be a cosine function. So, the derivation is not within the scope to show you. It could take me hour and a half, and I have to look at the notes in order to copy it down on the board, but that is not the important thing. So, the non-dimensional the solution, now I will give you straightforward the solution of the temperature field is the non-dimensional temperature field, which I have defined as T1 minus T by T1 minus T0, and that is equal to 2. And let me see if I can write it without seeing my notes. So, this is n is equal to 0 to n is equal to infinity, and then we have minus 1 to the power n plus half, and then I get the first term exponential, and this is with respect to the non-dimensional term, then minus n plus half, and then I have squared pi squared tau. Okay. And then we have the cosine term, which is now n plus half into pi, and my non-dimensional distance is this. That is the solution. I got it right. And this is the f1 exponential function and the cosine function. The distance appears as cosine function. So, now for example, if we had two different distance, two-dimensional problem, I could have again not just one cosine function, I have another cosine function, because the moment I put in another space derivative, then what happens is for space I see that cosine function comes, for time derivatives I see exponential comes. So, even if I do two-dimensional unsteady problem, I will have three such functions, but two functions are going to be identical because they are governed by the same type of derivatives, that is the second order derivatives. So, let us not talk all about this. Now, if we look at now the solution of this equation, let us represent this in terms of so let us look at what it is. So, I should be able to, since t, t1, t0 all unknown, you can find out here, for example, this is an infinite series. So, you will require your calculator in order to compute this, and what you are going to get, you can say, for example, let me see, at tau is equal to 0.1 at that particular non-dimensional time for various values of eta from +1 to -1, what is the temperature. So, you can compute the value of this, and then this will keep on changing depending on whether you put +1 or -1 or any intermediate value, and you can obtain that what is. So, you have to do a large number of calculations in order to find the distribution of non-dimensional temperature between. Now, the first figure is known. So, everywhere we can see that the temperature here is, so initially it is 1 and the boundary temperatures are 0. So, the temperature within this domain are going to be varying as between 0 and 1 itself, and that can be found out. So, if I, for example, if I say that this is what I want to find out at this particular point at time t is equal to 2 seconds. So, I will find out that what is the corresponding non-dimensional time for 2 seconds, because I will put alpha value is known, b value is known. The moment I put t is equal to 2 seconds, I will get my corresponding non-dimensional time. I will substitute this. So, everything is known here except n, which I have to compute within the summation, and then this represents a point where y is equal to eta is equal to 0. So, I will substitute this term eta is equal to 0, and this becomes is equal to cosine of 0, which will always become equal to 1. So, at that particular point, by computing the summation, I should be able to find out what is the temperature. So, one can have to do a large calculations, and therefore, you will really require a computer in order to find out the total distribution of it is, of course, going in this particular direction. There is no variation along this direction. So, it is either this or this. So, it is all identical here. So, in this direction, these are redundant directions. So, whatever I have drawn here does not matter. It is actually in this particular direction that this is eta is equal to 0, then eta is equal to 0.5, then eta is equal to +1, eta is equal to 0, eta is equal to -0.5, then eta is equal to minus. So, on this series of points along the y direction, you should be able to find out by putting in different time or the time dependent temperature field within the one dimensional domain can be found out through this particular equation or expression. Now, let us look at the slab geometry, and we can have, for example, you must understand that even without solving the equations, you must have certain idea about the nature of the temperature field within the system. For example, because this is a symmetric object, boundary conditions here and here are identical. This is plus b, or this is -1, this is +1, the dimensions are equal. So, therefore, we will have a symmetrical temperature profile between this, and the gradient of the temperature here at the axis at the symmetry line will vanish. So, that sort of a feature must be obtain once you solve this particular or compute this particular expression. Now, if you look at this, I will draw it in a big way, a relatively bigger size. So, this is the axis of symmetry. Okay. And then you can see that in one case I will get, and you should be able to tell me now, this is, I have not drawn it symmetrical. So, this is, and in another case the temperature goes something like this. That is how the temperature is. So, two different graphs I have shown you. Okay. So, this is the temperature, how the temperature varies, and as you can see I have drawn it from my intuition, or I know that it is symmetrical. So, that is why the gradient has vanished at this particular point, at this particular. This graph you should be able to see that this is a long time solution of this particular, because what is the steady state solution? The steady state solution, this essentially tells us that this temperature, this is actually non-dimensional temperature of 1, and this is the non-dimensional temperature of 0. Okay? So, this tells us that everywhere except for this small region, everywhere the temperature is close to the initial temperature, which essentially means that the heat has not been able to penetrate into the domain, which means that means I am talking of a time which is very close to 0. So, this is a small time solution. On the other hand, now 0 everywhere, which represents this particular line, the temperature that I have shown here, which is this line, this is very close to the uniform temperature of 0, which essentially means that we are talking of a large time solution here. So, you should be able to simplify on the basis of this, that if you have a large time, because this is a negative term, exponential of very large time, this time is going to vanish. Okay, it is going to be 1, and then the calculations are going to be very, very easy. For example, if you want to find out at large time what is the temperature at the central line, this will be, you do not have to really spend much time, and you will be able to find it. So, short time solution and large time solutions can be obtained by doing certain simplifications to this particular expression, which I am not going to discuss. But the most important point here is that, so this is an intermediate time graph. T is, time is almost is equal to 0, is this particular line. Time is somewhat less than this particular time, but it is greater than that, but it is certainly, it is more than. So, if this is, I would say arbitrarily, if this is 10 seconds, this is 0, this could be 30 minutes, and this could be about 4 hours. That is what is the typical value one would expect, that after 4 hours we are seeing that the temperature has become more or less homogeneous in the system. What is important here to note is that the slope of the line at the surface on the curve is changing as a function of the time. If you draw a tangent to these curves at the surface, whether you draw it on this side or you draw it on the other side, it does not matter because it is symmetrical. So, the slopes are drastically different. Okay? So, you can see, for example, for this particular line the slope is very steep, then the slope decreases, and then the slope further decreases, and ultimately the slope becomes equal to 0 at large time itself. And what does this slope essentially indicate? This slope essentially indicates that it is the flux of heat. Okay? So, I am evaluating, so it is slope of the line, and if I multiply this, and if this represents my y, for example, then multiplied by k, and this is at y is equal to 0, that basically is the heat flux, heat entering through the surface into the one dimensional domain. So, the slope that the dt k is constant, and that the slope is changing as a function of time, which essentially tells us that the heat flux is changing as a function, which is a time dependent heat flux, which is really, so you cannot really calculate, you can calculate an instantaneous heat flux, of course, okay, but if you want to find out a total heat flux, in that case you can say that the average heat flux in that case is to be determined in terms of we call it a time averaging of the heat flux, and T is equal to T1 and T is equal to T2, and this is Q, which is a function of T. So, if you differentiate this particular term for long time or short time, you should be able to find out that what is the derivative, multiply it with k, and then you can get an instantaneous, you can get a term which will be in terms with tau. Okay? And then you should be, I have written it for example, in dimensionless case, so you can have a non-dimensional heat flux also here, but then eventually you have to get it into the dimensionless form. So, once you get several such flux, at 1 second this is the flux, at 2 seconds this is the flux, at 3 seconds this is the flux. Now, you have what you have to do to find out an average heat flux, you have to carry out a time averaging in which T total essentially represents T2 minus T1, that is the span over which you are doing time averaging. And time averaging, I have also introduced this time averaging concept when I was talking about time averaging of Navier-Stokes equation, particularly in the discussion of turbulent flows. So, this is a finite slab which for which an infinite summation series has been shown to be the solution, and for 2-dimensional and 3-dimensional objects also the similar summation series solutions are available, which I urge that you can go through one of the books which I have listed today on the board, and that will give you an idea about. So, it is a one sum essentially indicates a single 1-dimensional problem. If you have 2 sums, okay, which will be telling you that it is unsteady state 2-dimensional problem, and 3 summations essentially will tell you it is an unsteady state 3-dimensional scenario. The other important problem in 1-dimensional, now before I move on to the other important problem, I must say that I have shown this with regard to a Cartesian coordinate problem. Equivalent problem can be derived, for example, or solved for example, cylindrical coordinate system, and in that case the solution is going to be not like the summation series, but you will get solutions with a characteristic Bessel function. So, Bessel function solution comes from cylindrical geometry, and that you can really see or similar kind of solutions in the textbook that I have. But those are I will take much longer time to introduce all these particular cases. So, therefore, I will stop as far as unsteady state heat conduction in 1 dimension or 2 dimension is concerned. We will talk about a different geometry which is of interest to us, okay? And that is called a semi-infinite geometry. This is an interesting proposition. So, it is still a 1-dimensional problem, okay? So, those condition applies here, 1D constant property, we have no source and unsteady state. This slab geometry which I have shown here, okay, which has a width of 2b, for semi-infinite geometry we can say that the one of the wall is finite and the other wall or the slab thickness itself is so large that you really do not see where the other end of it. So, it is finite, it is here, but it is infinite on the other side itself. That means, because in reality this kind of a domain is non-existence, but this is the reality because of the phenomena which is involved. For example, you can imagine that suppose most importantly you will understand it. Suppose if this is a steel bar, it is a steel slab, because you do not know what is the value of thermal conductivity, etc., but you know because you are a metallurgist that what is the value of diffusivity. You can imagine that if I put, I have a process which is 3 hours long process, the slab is this thick, I want to carburize it. So, the carbon from the surrounding enters the slab. Okay? Now, you can imagine, because the diffusivity of carbon in steel, solid steel is so low, of the order of 10 to the power minus 10 meter square per second, carbon will take maybe more than 8 months to reach this particular surface by diffusion from this end, or maybe even longer. You have to do really a calculation, that kind of a calculation we will do. So, therefore, even though the domain is finite, the phenomena which is taking place is so slow, as a one dimensional phenomena which is taking place is so slow that it does not recognize the presence of the wall at the other end itself. So, for all practical purpose, we can say that this wall is actually at a distance of infinity with respect to the origin, which may be taken to be x is equal to 0. Okay? So, because it is a one dimensional problem, the same governing equation will apply. So, we will say last problem I introduced, I wrote it y direction. So, the slab was in this particular direction. Now, I am writing the slab to be in the x direction itself. And the governing equation is same, but now the geometry has changed. So, the boundary conditions have also changed, and I will write down the boundary, that will be the starting point. So, we will take this equation. So, I hope you understand that what is the meaning of a semi-infinite geometry. It is a mathematical approximation of a real life scenario when the domain is such, or the domain is so large that the diffusing species or the diffusing entity do not see the other end of the domain, and in that particular case even a finite domain can be treated as an infinite domain. And I will show you that, if this slab is taken to be very, very large, the center temperature can be predicted from infinite series, and the center temperature can be predicted from the solution what I am going to outline, and they will match together because I have taken the slab to be enormous. So, the heat from here is not able to penetrate to the center, and the same philosophy applies here, that heat from here is not able to reach here because the duration of the process is so small and the diffusion coefficient or the thermal diffusivity of heat is so low. By the by, you must understand, you must note down that if you take the ratio of alpha to d, alpha is the thermal diffusivity and this is the mass diffusivity. We will of course do mass transfer, but we must understand that alpha is larger at least by 2 orders of magnitude than d. So, that means heat is diffusing, always mass is lagging and heat is advancing. So, heat flow is taking place faster than the mass flow, which essentially means that if you have a simultaneous heat and mass transfer problem, you will see that the heat transfer will get to the steady state much earlier than the mass transfer itself. So, we will continue this tomorrow.